Alright, here we go with homegrown homework videos. This is chapter 1 review, and we'll just kind of run through these and pick up um, things that you might not remember and need some help with. We'll talk about those, and we'll also just do the problems. Alright, so this is number 1, 6, and 11 we got on this page. So we want to, number 1, find the equation of a line with slope 2. So slope is 2 and the x-intercept is 5, so that means that goes through the point 5 comma 0. So the general equation for writing, formula for writing the equation of a line is y minus y1 equals m times x minus x1, where x1, y1 is a point on the line and m is the slope. So since I know a point on the line and I know the slope, I can just substitute it in and I get y minus 0 equals 2 times x minus 5. And we are always welcome to leave our answer in that form, knowing full well that if I ever want to write it in slope-intercept form, I can just do some basic algebra to get to y equals mx plus b form. Alright, number 2. A cubic polynomial. Okay, so cubic. That means it's the third degree. And the thing to remember here is, in general, if I have a polynomial that crosses through the axis like this, say it crosses through at the point 3, then that means that x minus 3 is a factor. Oops. Okay. But if however it goes like this, over negative 2 say, then x plus 2 is a factor, but it's actually a squared or a fourth power, an even power. Because think about this. When I have x minus 3, if I plug a number in less than 3, like 2.9, 2.9 minus 3 is negative, and 3.1 on this side, it's positive. 3.1 minus 3, it's positive. So this factor here crosses the axis when it has a odd power to it. When it has an even power, if I plug in a number, for instance, to the left of it, like negative 2.1, negative 2.1 squared, or negative 2.1 plus 2 is negative 0.1 squared is positive. And I recognize it's negative, so hang tight with me on that one. On this side, negative 1.9 plus 2, if I plug that in there and square it, it's positive also. So if I actually make this a negative on the outside, then do you see that whether I plug a point on either side close to negative 2, when I square it and then make it a negative, I'll have negative points on both sides, oops, of my 0 there. Okay, so for 6, if we want a cubic polynomial, and I know the x-intercepts are 1, 5, and 7, I can immediately say it's going to be something like this. X minus 1, x minus 5, x minus 7. And I don't know if what it might look like, so I got 1, 5, and 7. If it does something like this, then it would look just like that. Alright, does that make sense? This squared situation here would show up something like this. Let's see here. If it went like this, down, touch, and then like that, then this would be my one term. You know, if this was 4 and this was negative 1, this would be x minus 4, because that's what makes that term 0. And this one would be x plus 1. Well, if I left it like that, also I'd only have a quadratic, you know, degree 2. But like I said earlier, this has to be a squared term because the values on both sides are the same. Okay, so this would be an example of this. Okay, so these are just possible cubics that have, or this is a possible cubic that has those 3 roots. All right, let's take a look now at number 11. 11. The entire graph is shown. I'm going to make this smaller so we can see it. The graph, which I put on a different picture here. Yeah, sorry about my cheesy pictures. The entire graph is shown on 1.98, which is this graph right down here. And they say, what's the domain? So looking at this, the domain are all the x values that are used. It looks like it goes from 1 all the way out to 7. So A, the domain, or I'm sorry, did I say 1? I meant 0. Sorry about that. 0 less than or equal to x less than or equal to 7. B, the range would be the y values. So it looks like the smallest y value is -2 all the way up to, well, we'll call that 5.5. How about that? -2 less than or equal to y less than or equal to 5.5. List all the zeros. The zeros are where it crosses the x-axis. 0 happens when x is equal to 5. D, the intervals where it's decreasing. Decreasing, the function from right to left is going downward. All right, so as we move from right to left, the y values are always getting smaller. So that's decreasing on this interval. 1 less than or equal to x less than or equal to 7. And then E, E, where is it concave up, or is it concave up or concave down at 6 at this point right here? Well, concave up, I think of it as if it holds water if you were to complete the curve and pour into it. Concave down. Okay, so this graph right here is actually concave down all the way to about right in here, and then it switches to concave up. You see that? Because if you finish the curve, it would hold water, is one way to think of it. So E, is it concave up at x equals 6? Yes. And F, what is f of 4? F of 4 is approximately 2. Oops, if I drag straight across there, approximately 2. And G, is it invertible? In other words, does F have an inverse that is also a function? Okay, and the answer is, I'm going to erase this. Say, remember, the inverse is what we get when we switch the x and the y's. And I want to know if that's a function. Well, the graph of it is what we get when we reflect it across the line y equal x. So if I do that, that looks like it's going to go, these are always tough ones to do, like that, and then this here reflects this way. It's going to somehow come like that, sort of. So it's going to look like it's going to be something like that. And this definitely comes up, well, 3. I guess it's probably going to be a little bit longer. I didn't draw this exactly, this 45 degree, but it's going to hook around. And is this graph right here a function? And the answer is no, because for this x value, I got 2 different y values, right? Okay, so no. Let's do it like this. Some x values would have more than one y value. Okay, does that make sense? All right.